Yo, 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 Mr. Tran here with another video lecture. Today, I'll be talking about solutions. If you are not part of the solution, you are part of the precipitate. Please be sure to take your notes in your booklets. If y'all left it at the school, just take notes on any paper that you can refer back to later if needed. Here, we have a review of terms we've learned in the first semester of chemistry: element, compound, and mixture. Let's concentrate on the mixture. It is a combination of more than one pure substance. Salt water is made up of sodium chloride and water, while there are many things that are mixed together to make a salad. We can further break down a mixture and classify the substance as either a heterogeneous mixture or homogeneous mixture. Remember, the main difference between the two is what you can see. Same is homogeneous, different is heterogeneous. There were separation techniques that we learned as well. There are three ways to separate mixtures. Number one, distillation, which is just the separation by boiling point. Number two, filtering, which is the separation between solids and liquids. And finally, chromatography, which separates based on the ability to dissolve. There's only one chemical mean of separation, which would be electrolysis. So you've been hearing this word solution, but what does it really mean? A solution is simply a homogeneous mixture. A solution has two parts to it: the solvent and the solute. The solvent is defined as the most abundant or dissolver. The solute is defined as the substance being dissolved. So let's take a look at an example. Here, I have salt water. You can see the picture. Tell me, what's the solute? Very good! It is the salt, and thus making the solvent the water. Substances have different characteristics. Some are considered soluble and some insoluble. Soluble is defined as a substance that can dissolve completely, so that the solution looks transparent. Insoluble is defined as something that does not dissolve completely. This type of solution would look cloudy. So in our picture below, the clear but colored solution is considered soluble, while the cloudy white solution is considered insoluble. So how do substances dissolve? Well, polar water molecules are always moving and will collide with each other and other molecules. There's a simulation below and you can find the link on Canvas. However, I will illustrate the process on the next slide. Let's draw how salt dissolves. NaCl splits into sodium. I'm just going to make it orange. And chloride. I'm going to make it green ion. So let's draw it out as well. We have sodium and chlorine. So we also want to look at water structure. Water is consisting of one oxygen and two hydrogen atoms. We know that water has partial charges within its structure. Oxygen, when it becomes an ion, gets a -2 charge. So I'm going to denote that by drawing a partial negative. And again, it is two negative charges on oxygen's side. And on the hydrogen side of water, we know hydrogen becomes a positive ion. And so I'm going to draw the partial positive charge, one for each hydrogen. And there we have it. The oxygen side of water is negative and the hydrogen side of water is positive. Let's review the properties of attraction. Opposite charges attract each other. So if an ion is considered positive, it will attract negative ions. So let's take a look at water and apply it to how it would attract towards these ions, Na plus and Cl minus. Which ion will the oxygen side of water attract? Remember, oxygen is negative. Negative attracts positive charges. You are correct! The sodium ion. So let's draw water molecules attracting sodium ion. To do this, I need to have my water facing sodium with the oxygen side towards sodium. So I drew my 3 oxygen and I'm adding hydrogen. I'm only drawing 3, but note that it would surround the sodium ion. And now let's take a look at the hydrogen side of water. Which one would it attract? Obviously, the chloride. So how I would draw it would be to draw my hydrogens first. And again, I'm just choosing 3. 3 is just an arbitrary number. I could have picked 2. And filling in my oxygen. Okay, so this is how we draw the separation of salt and water. Make sure you have a copy of this drawing in your notes. Complete the dissociation of the following salts. I'm going to split the ionic compounds into their respective parts, positive and negative. So I'm going to start off with potassium chloride. It splits into K plus and Cl minus. Next, I have magnesium chloride, and so magnesium is a positive 2 charge, and it splits into 2 chloride ions. So where am I finding these charges, y'all? Like I said, you can't forget the charges we've learned in the third 6 weeks. So it's on the periodic table. I'm drawing it real quick here. And we ignore this part, so squiggly. So we have a positive 1, positive 2, positive 3, skip, negative 3, negative 2, negative 1, and 0. So that's a little drawing for you guys as a quick reference. And let's move on to aluminum chloride. So aluminum chloride splits into aluminum is positive 3, and there are 3 chloride ions. And now we have a polyatomic. We can't split P and O up. We have to keep them together. So calcium is a positive 2 charge. And we have 3 of them. How did I get the 3? I got it by looking at the subscript. Now, looking at the PO4, so that's the polyatomic ion, and it has a negative 3 charge, but there are 2 of those. So that's splitting them up into their respective ions, or dissociation. Which substance were able to conduct a current based on the simulation? Since we didn't see the simulation here, I will tell you that it was the ionic compound. There's a keyword you need right here. Electrolytes. Electrolytes are defined as particles that conduct an electric current. Must have mobile charges in order to do so. This means it must have free positive ions and negative ions suspended in liquid in order for the electricity to travel or conduct. Non-electrolytes are substances that do not conduct electricity. Water's polarity allows water to split ionic compounds into their respective ions. Which compound would be the best electrolyte? So, this is determined by the ionic compound that releases the most number of ions. So let's work it out. We have NaCl. We know it splits up into Na plus and Cl minus, and that's a total of 2. Easier way is just to count the subscripts, y'all. So looking at the subscripts, they're both 1. It adds up to 2. So the next one, I'm going to count up the subscripts, is 1 plus 3 gets me 4. And here, y'all, remember, this is a polyatomic ion. You can scribble it out and just put X, and that represents a particle. So how many ions does it release? It has 3 plus 2 gets us 5. So the best electrolyte would be magnesium phosphate. Liquids dissolving liquids. Liquids that are soluble in one another are considered miscible. Let's repeat that. Miscible. It's easy to remember, y'all. Like dissolves like. Polar dissolves polar. Nonpolar dissolves, like you guessed it, nonpolar. We can see examples here on the side. So these two aren't mixing because, again, water and oil do not mix. Factors affecting rate. First factor is the amount of surface area or particle size. The greater the surface area, the faster it dissolves. What does this mean? Greater surface area means the property of the substance to be exposed to water. Let's take an example to illustrate this concept. We have a cube of sugar versus ground sugar. That's the sugar that you guys use from the packets at Starbucks. Which one will dissolve in water faster, the cubed or the ground sugar? As you guessed it correctly, the ground sugar. That has a greater surface area than the cubed. How the cube would have dissolved would be, and I'm illustrating this in blue, that the water can only touch the surface first, and then it eats away until it gets to the core and breaks all the sugar apart. The ground sugar, each individual particle or grains is exposed to water, so all of it is dissolved at once. The second factor is temperature. Most solids dissolve faster at higher temperatures. That's easy to remember, y'all. Heat them up, speed them up. Heat them up, speed them up. Heat them up, speed them up, heat them up, speed them up, heat them up, speed them up. The particles are moving faster and colliding more with each other, and that's how ionic compounds dissolve in water. So those water molecules bounce off of the ionic compounds and it breaks it up. More collisions means more ions released. Finally, we have agitation. This is considered stirring or shaking. So if you see the word agitation, it simply means the same thing as stirring or shaking. This will speed up dissolution. Stirring the sugar and water will cause it to dissolve faster because we are moving and having more collisions than just letting the sugar sit in water. Again, water is moving, but very, very slowly. So to speed it up, we can, again, stir the water. Next up, we are going to talk about concentration. Some of you might ask, what is concentration? Simply put, it is how much solute is in a certain amount of solution. When we see concentration, we tend to think about the 3 different types of solutions. First, we have what is called unsaturated solution. It is a solution that is able to dissolve more solute if more is added. The second type is a saturated solution. This has the maximum amount of solute. So if you add any more, that solute will not dissolve in the solution. And this leads to our third type, a supersaturated solution. And again, that is a solution that has dissolved excess solute, but only at a higher temperature. So if we add it at a cooler temperature, it won't dissolve. To understand this concept, we need to define solubility. Solubility is the amount of solute that will dissolve in a given amount of solvent, usually water. There are factors that affect solubility. First one is the nature of the solute and solvent. Different substances have different solubilities determined by the type and strength of bonds between the particles. This comes with the fact that polar particles dissolve in polar solvents. Like dissolves like. The second factor is temperature. Most solids become more soluble as the temperature of a solvent increases, but gases are less soluble in liquids at higher temperature. Why, you might ask? Well, remember, gases move faster than liquid, so there's no way gases can stay dissolved in liquid if the temperature increases. And think about a hot summer day here in Houston. I'm outside and I decide to buy a can of Coca-Cola. Oh wait, I'm changing that to Dr. Pepper. Just joking, of course it would be Mountain Dew. So I drank half of the Mountain Dew because I have finally learned not to chug the soda, and left the can out in the sun. I came back to it only 10 minutes later, and what do you think happened? You are right! The soda is completely flat. The gas has left the liquid. So again, hopefully that will help you guys remember that gases do not stay dissolved in liquid at high temperatures. Third factor would be pressure. When we see the word pressure, we are only going to think about the solubility of gases. As pressure increases, the solubility of gases increases. Again, the soda can example will illustrate this point. The reason we hear the sound is because there was pressure pushing on top of that liquid, keeping the carbonation in solution, and when we open that can, it releases that pressure, so decreased pressure allows the carbonation to escape. So when we are looking at solubility diagrams, we are looking at how soluble a substance is in 100 grams of water at a certain temperature. You can determine whether a substance is considered saturated, unsaturated, or supersaturated based on the point on the diagram. Saturated is considered to be a point on the solubility curve. You will see what this curve looks like on the next couple of slides, I promise. But for now, bear with me. Remember, saturated is on the curve. A substance is considered unsaturated at a point below the solubility curve. Supersaturated is a point above the solubility curve. Again, you will see an example of what this curve looks like on the next slide. So what I want you to do is to be sure to graph this in your notes. You may want to pause now and replay after plotting. You're plotting the table. Don't forget to label your axes. So the maximum amount of solute dissolved in 100 grams of water is tested at 4 different temperatures. You just graph these points right here. Then the data points are connected by a line or curve. This right here, y'all, is the solubility curve, that line you see. The curve occurs between 0 and 100 degrees Celsius. Why is this scale only between 0 and 100? You guessed it correctly. These solutes are being dissolved in liquid water, not ice, not water vapor. At 40 degrees Celsius, 100 grams of water can dissolve in how much solute? So how do we get the answer? We start off by going to 40 on the x-axis And then we're looking for where on the y-axis the curve is. We got the point, we follow it over to the y-axis, and it looks like it's approximately 44 grams. Some may argue 45 grams. Your assessment will be multiple choice, so just pick the one that is closest to your interpretation. The next problem. Will 50 grams dissolve in 100 grams of water at 75 degrees Celsius? Let's plot these values. Going to 50 grams on the y-axis, we meet with 75 degrees Celsius. We have a point. It is now below the solubility curve. So the answer is yes. It is unsaturated, and by definition, we can dissolve more solute. Remember, any point below the curve is considered unsaturated. Is a solution with 70 grams of solute dissolved at 40 degrees Celsius saturated, unsaturated, or supersaturated? Remember, we must plot our point first. So 70 grams meets 40 degrees Celsius. We have our point. That point is above the graph, so it's considered to be supersaturated. Remember, for any point above the solubility curve, the solution is considered to be supersaturated. So these questions are going to be answered on the next slide. At 60 degrees Celsius, 38 grams of solute is dissolved in 100 grams of water. What is the name of the solute? So we have 38 grams meeting 60 degrees, and we're looking to see where those 2 points meet on a line. So again, we have 38, and I'm plotting 38 right here, and it's meeting 60. So where those two intersect, looks like it's a close call between sodium chloride and potassium chromate, the light blue line and the purple line. I'm going to make a judgment call and say it is sodium chloride. On your assessment, it won't be this close, so just make your best judgment. Number 2, I have, if 50 grams of potassium chloride are dissolved in 100 grams of water at 80 degrees Celsius, is the solution saturated, unsaturated, or supersaturated? So let's plot the points and see where it lands. I have 50 and 80, 50 grams. I'm going to mark this in red, and 80. Moving to meet it, I'm plotting my dot, and I need to know which substance I'm looking at. The problem asks for potassium chloride. So potassium chloride is a dark blue line, circling it in red here. That point is below the curve. So below the curve means unsaturated. Number 3, we have, what is the solubility of potassium nitrate at 45 degrees Celsius in 200 grams of water? Whoa, whoa, whoa. There's something different with this question. 200 grams of water. But wait a minute, Mr. Tran. This diagram is only for 100 grams. So how do we solve this? Very good question. We will simply solve it the normal way, as we did in number 1 and number 2. And once we have the answer, we simply multiply that answer by 2. So we go to 45 degrees Celsius, purple. I'm going to move up this purple line until it meets potassium nitrate, which is the green line. And again, moving, and finally it hits. And I'm going to go over to the y-axis. Looks like it is 75 grams, but remember, we need to multiply 75 grams by 2, which gets me 150 grams of solute. So that's the answer, 150. Number 4, what is the solubility of potassium chloride at 80 degrees Celsius in 150 grams of water? Same way like the previous problem, we will simply multiply our answer by 1.5. So let's take a look. 80 degrees for potassium chloride. So 80 degrees, overlapping, 80 degrees for potassium chloride. Potassium chloride, again, is that dark blue line, meeting it here and moving it over, and it looks like it is 52 grams. But I need to multiply 52 by 1.5, and that gets me 78 grams. What trend do you see as temperature increases? So we're looking at this graph, and we see most of the curve goes up. What this means is that the solubility increases for most salts. Remember, salts is just another term for ionic compound. Which two salts decrease in solubility as temperature increases? So we're looking for a curve that goes down, and that would be ammonia, NH3, and we have cerium 3 sulfate. And that is the Ce2SO4 3. Last but not least, which salt has the least or most change in solubility? So least means that it will be close to a flat line. That looks like sodium chloride. So let's write that down. Least change would be sodium chloride. And the most change, we're looking for the steepest curve, the one that looks like it's flying up to the sky. That one would be potassium nitrate. Gas solubility. In terms of pressure, we have Henry's law. As pressure of the gas above the liquid increases, solubility of the gas increases as well. We see this demonstrated in the picture. The purple dots are the gas particles within the piston. The piston is this, and there are more purple dots in the water after the piston is lowered. When the piston is lowered, that means there's an increase in pressure. And that is right there, increase in pressure. Concentration is calculated using molarity. We have the formula given to you here. Molarity is equal to the moles of solute divided by liters of solution. Here are some tips on how to solve these type of problems. If you are given mass, you must convert to moles. Yay, moles! If you are given milliliters, you must convert to liters. Units of molarity is always moles over liters. So if you have 2 molar, yes, that's right, 2 molar, M is molar, you have 2 moles over 1 liter. Same thing with 6 molar. That simply means 6 moles over 1 liter. Our first calculation problem. A potassium hydroxide solution with a volume of 400 milliliters contains 2 moles of potassium hydroxide. What is the molarity of the solution? Just like you've seen for all the calculations before, we will always list the given on the left-hand side in the order of the equation. M is for molarity, which we are solving for. Moles, we have 2 liters. We must first convert milliliters from 400 to 0.4 by moving the decimal place 3 places to the left. Next, we have our equation. We isolate. Oh wait, it is isolated. Then we plug in to solve, and we get 5 molar. We can now pause this to write down the work. Okay, moving on. A glucose solution with a volume of 2 liters contains 72 grams of glucose. If glucose has a molar mass of 180 grams per mole, what is the molarity of the glucose solution? The given is located on the left-hand side once again, and we go in the order of the equation. So we're solving for molarity. We are given the mass, so we need to convert to moles by simply dividing the mass by the molar mass or using dimensional analysis. So we have the railroad here, molar mass on the bottom, simply divide, and we get 0.40 moles. Again, we have our liters, 2 liters, equation, isolated already, plug in, divide, and we have our answer. You may now pause to write down your work. Last one. How many grams of potassium chloride solution are needed to prepare 2.5 liters of 0.50 molar potassium chloride solution? We do the same procedure. Write out the givens on the left-hand side. So I have my molarity there. I'm solving for grams, but our equation has moles. Luckily, we can convert from moles to grams. Equation time. So we need to isolate moles. So I simply do this by multiplying liters on both sides. And once I have the form, it is moles equals molarity times liters. And we have the plug-in portion, multiply, we get an answer. But remember, we want grams. So I simply take the moles and convert it to grams using dimensional analysis or simply multiplying by molar mass. So multiply and we get 97 grams of potassium chloride. Dilutions. So the definition is reducing the concentration of a solution by adding more solvent, usually water. The molarity and volume are indirectly proportional, meaning if volume increases, the molarity or concentration decreases. We have the formula above the test tube. M1V1 equals M2V2. You're going to love this equation. So the picture clearly paints the dilution process. We know the darker the color, the more concentrated the solution. So this has a lot of the solute in it, and this one has mostly water or whatever solvent was used to dissolve it. Mr. Tran, do the number of moles of solute change if the volume of water changes? The answer is no, Billy. We can simply plug in the units for each variable and see that the moles doesn't change. For M1, we can replace it with moles 1 over volume 1 times volume. Same thing with molarity 2, moles 2, V2. And you see that the volume cancels out and we have the moles not changing at all. We have our first calculation problem using dilution. A student dilutes 10 milliliter of 3 molar sodium hydroxide to 100 milliliter. What is the molarity of the new solution? We know that the word of connects the two variables. So of connects these two. Since this is the first set we see, I'm going to make it my V1 and M1 respectively. So given M1 is 3.0 molar, V1 is 10 milliliters. We're looking for M2, and my volume 2 is 100 milliliters. Next step is providing the equation M1V1 equals M2V2. I need to isolate V2 by dividing M2 on both sides. When we do that, we get M2 equals M1V1 over V2. Plug in our numbers. multiply and divide, and we get the answer. You may now pause this video to write down the work. Last but not least, y'all, making a diluted solution. So this is a very important skill to have. I developed this skill through high school and college, and I was able to use this in real life at a lab. So you have 1.50 molar stock solution of sodium chloride on hand, but you need 150 milliliters of 0.800 molar solution. How many milliliters of the stock solution do you need to create the diluted solution? Remember, stock solution is always the more concentrated solution. So I'm going to write this on top. Stock solution, more concentrated. So how much of that stock do we need? We need to use the stock to make very diluted solutions for quick steps in a lab. So simply plug in the values, y'all. I always use my stock solution as my first value. So given my stock is the more concentrated one, M1 is my stock, 3.0 molar. I'm solving for how much stock do I need to use in order to make my diluted solution. My diluted is my 2's, M2V2 respectively. We have our work, equation M1V1 equals M2V2. Isolate to get V1 by itself. I simply divide M1 on both sides, and that's what it looks like. Plug in and solve. I mean, now pause this video forever because we're done. So again, hope that you guys learned a lot about solution. Have a good one.